Hello, everyone. I'm presenting the work done by my esteemed colleagues, uh, Vish, Peter, Lily, and Ciel. I'm Alex, and this was all done under Professor Steve Mann at the University of Toronto. Our project is called Metaveillance Vehicle for Sensing Ultrasonic Sensors, a proof of concept for secure medical deployment in conflict zones. Um, the central idea is very simple. Instead of using a mobile robot only to observe an environment, we use it to detect the sensing infrastructure operating within that environment. In this proof of concept, a teleoperated RC vehicle searches for active ultrasonic sensing signals while improving live video and immediate feedback to a remote operator. Now, the motivation is that conventional surveillance can observe people, objects, and scenes, but it cannot necessarily reveal the sensors that are observing those same spaces. In conflict zones, temporary medical sites, or field clinics, ultrasonic devices can be deployed for tracking, monitoring, ranging, or triggering. And because their signals are outside normal human hearing and are not visually apparent, an ordinary visual inspection may completely miss them. A manual sweep also creates a safety problem. Sending a person into a hazardous, contaminated, or conflict adjacent area increases operator exposure before we can even know what sensing infrastructure is present. This leads to the technology gap addressed here, a low-cost mobile platform that can remotely search for and indicate ultrasonic sensing activity. Our aim is not to claim a completed field-ready security system. It is to demonstrate that mobility, ultrasonic detection, live video, and operator feedback can be integrated into one practical proof of concept platform. Now, the slide positions the work right here, as you can see, within the broader language of valence. Surveillance refers to undersight, whereas surveillance refers to oversight. Oversight, which is observing people from or environments from above, or from a position of authority, whereas surveillance is observing from below or from within the environment being observed. Metaveillance changes the object of observation. Rather than focusing on people, it senses the capacity to sense. In other words, it attempts to detect the sensors and sensing infrastructure themselves. We then use the term metaveillance for a mobile inspection process that combines metaveillance with movement through the environment. The RC vehicle is therefore not simply a camera platform, it is a platform for inspecting the infrastructure through which observation or sensing may occur. This framing, based on concepts introduced by Professor Steve Mann, is important because it shifts the question from what is happening in the space to what systems in this space are capable of sensing what is happening. The system has three main layers. First is the operator interference layer. A PC runs a Python graphical interface and sends JSON command packets over a TCP connection using a local Wi-Fi network. This gives the operator one place to control the vehicle, view the camera, and monitor sensor state. Second is the sensing layer. An ESP32 cam provides the live video stream. The ultrasonic receiver is based on an HCSR04 module, but instead of relying only on its standard trigger and echo behavior, we access its analog signal path and process that signal using an RP2040 microcontroller. Third is the mobility layer. Uh, an onboard Arduino receives motion commands and relays them to the VESC motor controller and steering servo. The architecture is deliberately modular. Propulsion, video, ultrasonic processing, and the user interface can be tested or upgraded independently while still operating as one integrated vehicle. The physical platform begins with a repurposed RC car. This gives us a relatively inexpensive, rugged, and mobile phase that can move through constrained or potentially hazardous environments. A custom 3D printed mounting phase plate separates the locomotion electronics from the sensing electronics. That separation reduces mechanical and electrical clutter and allows each subsystem to be modified without rebuilding the entire vehicle. The camera is mounted on a 2 degree of freedom pan and tilt bracket. This lets the operator look away from the direction of travel without repositioning the whole vehicle. The onboard components include the Arduino, BESC, ESP32 cam, RP2040, a LiPo battery, and WS2812B indicator lights. The lighting is not only decorative, it provides an immediate visible indication of detection state and supports the long exposure visualization shown later. Overall, the slide emphasizes that the platform is compact, modular, and built from accessible components. This is the technical core of the system. Standard HCSR04 is normally used through a digital trigger and echo interface. We instead tap the analog output of the onboard LM324 amplifier stage. This analog bypass allows the system to continuously monitor ultrasonic activity through around the nominal 40 kilohertz carrier rather than waiting for the module's normal ranging transaction. The RP2040 analog to digital converter samples on GPIO 26 at approximately 250 kilosamples per second using a clock divider of 191. That sampling rate is well above twice the 40 kilohertz carrier frequency, so it satisfies the basic Nyquist requirement. The raw signal can drift because of bias and changing conditions. We therefore apply a rolling bias estimate. The new mean is computed as 99.9% of the previous mean plus 0.1% of the new raw voltage. This slowly tracks our DC drift while preserving the faster oscillatory component that we care about. Data is visualized in windows of 400 samples corresponding to roughly 1.6 milliseconds. Within each window, the system estimates frequency with 0 crossings. The estimated frequency is the number of crossings divided by twice the window duration. Finally, we add temporal verification. A single noisy window is not enough to trigger an alert. The system requires 2 consecutive verified windows separated by approximately 3 milliseconds before asserting a valid detection. This pipeline is intentionally lightweight. It can run on the RP2040 without a heavy spectral processing stack while still combining high rate sampling, bias removal, frequency estimation, and repeated confirmation. The operator interacts with the system through a unified Python GUI. The interface sends JSON control packets over TCP to the onboard controller. It displays the ESP32 cam stream, the ultrasonic state, and information related to vehicle operation. Camera, pan, and tilt are controlled with WASD keys, while the arrow keys control throttle and steering. An important practical lesson was communication reliability. Early versions attempted to use Bluetooth, but the connection was not sufficiently robust for the integrated system. The design was therefore changed to TCP over a local Wi-Fi hotspot. This interface supports situational awareness by placing sensing and visual information together. When an ultrasonic alert occurs, the operator can immediately compare that event with the live camera view and the vehicle's current position, rather than treating the sensor output as an isolated signal. Evaluation at this stage is preliminary and qualitative, so we separate what has been demonstrated from what still requires statistical characterization. In bench testing, the analog tap and RP2040 acquisition chain responded to sustained 40 kilohertz activity while rejecting lower frequency mechanical disturbances. At the subsystem level, verified ultrasonic detections reliably triggered the intended visual response on the WS2812 indicator. The images on this slideshow show the qualitative change from the normal state to the alert after a verified sensing event. In integrated vehicle trials of the RC platform, camera stream, GUI commands, ultrasonic processing, and alert logic operated simultaneously without obvious subsystem interference. These results establish integration feasibility, but they do not yet provide a complete measurement of detection range, false positive rate, or end-to-end latency. Those quantities require controlled experiments across distance, orientation, environmental noise, and different ultrasonic sources. We therefore present this as a successful integrated proof of concept, not as a fully benchmarked detection instrument. The key result is that a low-cost RC platform can function as a mobile metaveillance tool. The analog bypass is central to that result because it exposes ultrasonic activity that would remain invisible if we only use this sensor through its standard digital interface. The platform also connects detection to understandable operator feedback. The SWIM, or sequential wave printing machine, lighting creates a clear visual record of sensing activity and long exposure photography. The image on the right illustrates how the vehicle's lighting can imprint the detection state over its motion path. From an applications perspective, the main value is operator protection. Remotely controlled platform can enter a constrained or potentially hazardous area before a person does. The main limitation remains quantitative validation. Future benchmarking must determine useful range, sensitivity to orientation, false positive behavior, and latency under realistic acoustic and mechanical noise. To conclude, this work demonstrates the feasibility of mobile metaveillance by integrating RC mobility, passive ultrasonic monitoring, live video, and teleoperation, as well as visible operator feedback. The platform continues to remote inspection by allowing a user to search a constrained environment without immediately entering it. More broadly, it extends metaveillance from a sensory stationary sensing concept into a mobile robotic system. There are four main directions for future work. First, multimodal sensing could combine ultrasonic radio frequency and visual markers to reduce ambiguity. Second, multiple passive receivers could support beam forming or time difference methods for spatial localizations, moving beyond detection toward estimating where a source is located. Third, cellular backhaul could support more robust communication beyond a local line of sight Wi-Fi. Finally, the same concept could be adapted to aquatic metasensor vessels or submarines for underwater inspection. The takeaway is that sensing the sensors can become a mobile robotic task. This proof of concept establishes the integrated foundation, while the next stage is rigorous qualitative and quantitative testing and localization. Thank you very much for listening.